Greetings and welcome, real life friends. You know what? We've been internet friends long enough. I like to think we're really algebra-buddies in here. Going over last night's quest where we were doing part 2 of properties of radicals. We learned this little thing about conjugates. So conjugates are not quite the same. They're not quite opposites. Because opposite would have been negative a minus b, right? This is the opposite of that. But a conjugate is just the middle term is different. And so these are conjugates. And the reason these were helpful to us is because we remembered the pattern a squared minus b squared. And I can use conjugates in order to get rid of a radical in a denominator when there's addition or subtraction in that denominator. This, by the way, does technically only work with square roots because the squares will cancel out with the square roots. And so to get rid of this, I have to multiply the bottom by 7 plus rad 2. And so that is the conjugate of the present denominator. And so the only thing I changed was the sign. Remember that when multiplying these, the fraction bar is a type of grouping symbol. All right, my kids are yelling. So let's see. So I have to distribute 7 rad 10. And rad 10 times 2 is plus rad 20. Ooh, that's reducible. We haven't had a lot of those show up with a late reducing. But look out, it still counts. And then in this denominator, it's going to be a squared minus b squared. So 7 squared minus rad 2 squared. And so I'll have 7 rad 10 up top. This is a good problem. Rad 20, what's the largest perfect square that goes into that is 4. And it goes in 5 times. All over, 7 squared is 49, minus 2 is 47. Whew, man, I got to do my tablet settings again. I might just take off the screen protector on it. I feel like it's, I don't know, starting to get messed up. So I've got 7 rad 10 plus 2 rad 5. I was kind of hoping that these would have ended up simplifying. Would have been cool. All over 47. And so this is my final answer. Now, sometimes the number in the bottom could simplify with one of the non-radical numbers. But if you were to try that, you would have to simplify it with both of them. All right, both of them would need to be divisible by or reducible by whatever number you're thinking of. In this case, it wasn't even close. Didn't work for either of them. All right, let's see. The orbital period of a planet is the time it takes for the planet to travel around the sun. You can find the orbital period P in Earth years using the formula P equals D, the square root of D cubed, where D is the average distance in astronomical units, AU. By the way, an astronomical unit is the average distance that the Earth is from the sun. We consider that to be 1 astronomical unit. And so it's a very earthy thing to do to, start using space measurements and base it off of the planet that we're on. But math is a universal language. So that unit would be perhaps different for a different society on a different planet. So here we go. Simplify the formula. All right. So if P is equal to the square root of D cubed, okay. All right. I was starting to think about other properties that we'll be doing in future lessons, and so I got stumped for a second there. We do know how to simplify that. I can find the largest perfect square that goes into D cubed, which is D squared. And so the simplest form, square root of D squared, is D times rad D. Yeah. And so there's a simplified version of the formula. Part B, what is Jupiter's orbital period? So 5.2 astronomical units. So if you could imagine 3, 4, 5... Earth would be hanging out here 1 astronomical unit away on its near circular but always elliptical path around the sun. Whoa, sorry. And so Jupiter is 5.2 times as far away. Did not know that. Thanks, Jupiter. Also, yeah, Jupiter, yeah, was it a SciShow video that just came out recently about the pros and cons of having a jerk neighbor named Jupiter that also helps us out, protecting us from asteroids, things like that. So anyways, what is the, okay, so if D is the 5.2, the distance, all right, let's plug that in and find P, the orbital period for Jupiter. And so I feel like I should commit to this one now. I don't know. I'm going to plug it back into the original. Just because that way I get to do 5.2 cubed. 5.2 to the third power is going to be 140.608. And that's going to be approximately, so I'm going to hit second square root and then second answer on my TI-30X2S calculator, and I get 11.86 is the period. And what units are those measured in? They're not astronomical units, it's in Earth years. And so these are in years of Earth years, right? Which is different than a Jupiter year, by the way. All right, so we kind of do things with square roots. They happen. Good, good, good. All right, simplify. Oh dear, none of them have the same radical. None of those are like radicals, but wait. This one I could break up. Rad 4 times rad 3 is 2 rad 3. And so then I could combine it with this one. So 2 rad 3s plus 6 rad 3s is 8 rad 3s plus 2 rad 6s. And so that's done. And I can't combine those two because rad 6 is not a rad 3. All right, cruising. Oh man, this is good. All right, I felt like I was getting bogged down there for a second, but we're picking it up. All right, distribute. Square root of 5 times 6 is 30. Notice I can multiply their insides because they had the same kind of radical. They had the same index, so to speak, minus 96. Guys, I'm not going to be able to think of a perfect square that goes into whatever 5 times 96 is. I'm tempted. 4 goes into it to 16. I'm going to break this down first. Okay, there it is. Tell you what, I'm going to write this as the square root of 5 because that is being multiplied. But 96 I could break up into 16 times 6 times rad x. I don't know if that's helping me here, but I was just trying to preemptively simplify. And sometimes I got to be careful doing that because what if whatever I get after I multiplied these two things, what if that somehow could have been further simplified? And so I would have ended up having to simplify it twice. So minus, all right, square root of 16 is 4. Square root of 5 times 6 is 30. And the square root of x. So I'm just combining all of the things that could not be simplified into one bigger radical. And I kind of like that because, hey, it happened to match the other radical. And so now I'm just doing 2 minus 4. It's -2. And I combined those like radicals. All right, last question. Here we go. And then I'm going to take a break. I've been recording videos all morning so far. Cubed root of 3 times cubed root of 4 is the cubed root of 12 plus the cubed root of 3 times the cubed root of 32. Is that going to be 90 plus 6 again? That's weird because we were just working with 96. Except, I need to find a perfect cube that goes into 96. Now I have a feeling it's probably going to relate to 12 in some way. So it's probably going to relate to that. I suspect it's going to be 8. 16 doesn't help me because 16 is a perfect square, not a perfect cube. It wouldn't cancel out with that. But 16 I was looking at in my mind and I was like, oh, 8 goes into that and 8 is a perfect cube. And so cubed root of 8 times cubed root of, I'm pretty sure that's 12. And so that's going to simplify to be 2 cubed roots of 12. And here is 1 cubed root of 12. Remember that the right? If there's no number in front, there's this invisible 1. And so 1 plus 2 is 3. Cubed roots of 12. Oh, man. All right, here we go. Very intentional lines here. Oh my goodness, that just was invisible the whole time. All right, this tablet is needing something. Oh, all right, I'm going to go eat some red grapes. Have a good day, friendos. Take care, take care.